Hello and welcome to my class. I'm Grolin Annalisi from ThinkMo Education. I'm currently a Cisco Technology lecturer. If you like my video, welcome to my study group. Or contact my teaching assistant. WhatsApp account is +6 5834444290. Today's topic is switch principle, VLAN and VTP. Let's talk about the technical knowledge of the exchange network from today. As of last class, we have already finished talking about routing knowledge. Includes static routing, IGRP, and OSPF. Before we formally explain the technology of the exchange, first of all, we need to develop the entire network. Make a simple understanding. Because when we talk about exchange today, we must mention a device. Is the switch. So how did the network evolve step by step into what it is now? It is known intranet. Switches are very common. Even switching technology for enterprise networks is much more common than routing technology. Then why should there be such a technology? Including how the switch has evolved. I'll draw a picture to explain. Assuming these are the original two PCs. At the beginning, how should the two PCs be connected? It is known. A device wants to transfer data with another device. They are connected by a physical transmission medium. Actually, before the web, all computers are standalone. At that time there was no network cable, no network card, no protocol stack. The overall data transmission is through CD and floppy disk. After a period of time, with the innovation of web records, the network cable appeared. Network cable as physical transmission medium. We can pass data in the middle. Secondly, there must also be a network card on each device. Like switches and routers. The interfaces on them are called network interfaces. The one on the PC is called the network card. Then network cable plus network card. Plus running the same protocol stack on the device. That is what we call the TCP/IP protocol stack. These three constitute an element. We call it the smallest network unit. They can officially start data transmission. I give a simple example. For example, now this cable carries the overall bit stream. That is electrical signal. Similar to when we call in analog signals carrying voice streams such as. They are responsible for the transmission of signals. Then for the network card. After the network interface receives the incoming bit stream, it converts these bit streams into data. Sent to the protocol stack for processing. Including when it sends data to the outside world. It is also the network card that converts the data into a bit stream. And then sent out. That's like the TCP/IP I just mentioned. I mentioned this when I talked about the reference model before. We are talking about OSI. But actually we are using TCP/IP now. They are equivalent to communication language between multiple devices. That is, in the process of realizing the communication, including analysis of the data, addressing including future addresses. Because the three layers can do addressing, including our control over data traffic. All the same. Here's some of what it does. But with the development of the network, slowly there are problems. Between two PCs. We can't keep them close together forever. Network communication cannot be one computer to one computer. They are very close. Sometimes, we're going to involve some remote data access. Then there will be problems. The transmission medium such as network cable has the upper limit of transmission. The longest effective transmission distance of the network cable is 100 meters. If the two computers are too far apart between the terminals, Once the transmission limit of this network cable is exceeded, then the data starts to be lost. This is what we call lost packets. Your data signal is unstable. Data can be passed, but there will be packet loss. So not now. We will have a way. Add a repeater between these two devices. Just give it a signal amplification in the middle. I draw a device here. This is the repeater. The relay season can complete the amplification of the data signal. Equivalent to. The repeater has received data here. After receiving, it's going to be an integration. Then amplify the signal. Send the signal again. Then it can extend the transmission distance of the network cable. But this device has a problem. That is, it has only two interfaces. It has fewer interfaces. Two interfaces are not enough, because it can only amplify the signal of two devices. Look at me as an example. It has only two interfaces. It won't work if you connect another device here. You can't connect a third device. So there's the next generation of devices. After the repeater is the hub. To us, the two interfaces of the repeater are not enough. Let's change a device now. Called a hub. We still put it between the two devices. Then it is called a multiport repeater. It's no different from a repeater overall. There are more interfaces. So, we put it here now. This is a multiport repeater. A multiport repeater means it can now connect to more devices. Then we can complete the data interaction between multiple devices. Let's briefly talk about how it works. If the hub is now from an interface, received a data, it will directly send a copy from other interfaces. So it's a repeater. That is a working principle of multiport repeater. Well, first thing to know. It is a device working at the physical layer. Actually, it will only perform simple flooding processing on the data. This flooding refers to it received data from an interface. Copy and send a copy of other interfaces. For example, now this PC1 wants to access PC2. Don't want to access PC3. Then this data cannot be forwarded only to PC2. It will definitely send a copy to PC3. Because it handles all data. All other interfaces send a copy. So the hub does not recognize some of the upper layer. IP address or MAC address. So, it has no way to isolate the terminal. Everyone should know this. In fact, this kind of bandwidth utilization is relatively low. Because the bandwidth of the link is always occupied. Second, data security cannot be guaranteed. Hub-based networking. Unicast communication is not possible. So that's one of its downsides. We also call this device a hub. Half-duplex device. When you send, others cannot send at the same time. I should have mentioned a concept to you before. Collision domain. The data is within a certain range. If in the process of sending, data collision. This is called a collision domain. Then the half-duplex environment we are talking about is a typical collision domain. Now PC1 sends a data. In the process of sending, this PC3 cannot be sent out. Otherwise it is in a collision domain. The data will be incomplete. The data will be transferred from the original 0101. May be lost in the middle. A few digits are lost or become garbled. It's not complete. So this kind of networking environment is not okay. The transmission utilization rate is relatively low. Of course. We also said before. There is a technology in the conflict domain called CCNA200-301. It can solve problems in conflict domains. But it's too inefficient. So slowly we will find. We want to amplify the signal in the middle. I also want to connect multiple terminals in the middle. Also hope the collision domain isn't that big. Now there is no way to solve this problem. So how to solve it? We came out with a new device. The new device is called a bridge. A bridge is a small switch. You can understand it as is a data link layer product. Works on the second floor. The bridge has two interfaces. For the bridge, different interfaces are different collision domains. There will be no data conflict between the two interfaces. Let me give an example to explain the differences between bridge-based networking and hubs. For example, these two are bridge interfaces. In the meantime, they can send and receive data. Non-interference between the two. We can do this kind of work through the bridge. But the bridge itself has its own common problems. It also has only two interfaces. So the network is like this. A bridge in the middle. Connect two hubs next to a bridge. Then go to connect multiple terminal PCs. We can do it this way. To isolate the conflict domain on a smaller scale. You will find. Because this is the hub. So this is a collision domain. But since this is a bridge interface. So actually, collision domains are only so big. Probably originally 6 PC conflicts. But now you turn 6 PCs into 3 PCs conflicting. One of its problems is that it has only 2 interfaces. So the number of interfaces is not enough. Then the switch appears. A bridge works like a switch. It differs from the switch in that there are more switch interfaces than. We'll talk about how switches work in a moment. The latest products are now available. That is the switch we are using now. Suppose now this is a switch. What can a switch do? First of all, it has many interfaces. I can now connect other devices to this switch. I mark these PCs. 1, 2, 3, 4. 4 devices. Let's say this is the 4 interfaces of the switch. 4 switches. How does it work now? First of all, the switch is also a product of the data link layer. Works at the data link layer. There is a very core parameter in it, called MAC address. The switch can record the MAC address of the terminal, and can generate a table on itself, called MAC address table. What is stored in this table? For example, now interface 1 of the switch corresponds to a PC1 below. Suppose the MAC address of PC1 is a. It will generate such a correspondence. Let's say this is interface 2, interface 3, and interface 4. It is possible to store such information locally, followed by BCD. Their MAC addresses are ABCD. A table like this will be generated on the switch. Since it has a table like this, it can complete a precise forwarding of data. If now PC3 wants to visit PC2, the MAC address of PC2 is B. Then it's making a data request. Do you still remember the ARP we learned before? We can request to the other party's MAC through ARP. Complete data encapsulation. If PC3 now has the MAC address of PC2, it sends a data to the switch. The switch sees that its destination MAC is going to be. The switch will query the local MAC address table. It is found that B corresponds to its interface 2. Send data out from interface 2. Then this data came to PC2 alone. Then this data is for PC1 and PC4. They won't accept. The switch can complete unicast communication. And the switch is a full duplex device. The interface of the switch can isolate the collision domain. All devices can send at the same time. And receiving data is not affected. So in fact, you can understand the switch as combination of bridge and hub. A hub is multiple interfaces. There is also a MAC address table in the bridge. Works the same as a switch. It's just that there are few interfaces. It is an advanced hub plus a bridge equal to a switch. All in one. In the end, it became the equipment we use now. Same. Within each company. In fact, they are all similar network structures. If you want one company to communicate with another company, it is impossible for all devices to be connected to the switch. Including that we are now connected all over the world. It is impossible to network through switches. That's why we have such routers that are farther away and based on route forwarding. Eventually connect. This is the development of the web. I just want to tell you how the switch came from. Then we will start to formally talk about the content of the course. Today we talk about the principle of the switch. Here is a word. Ethernet devices including hubs and switches. These are the two most typical devices. Let's do a brief review. We just talked about hubs. For devices such as hubs, everyone must first be clear. Under what circumstances should we use such a device? I give an example. There is a PC down there. Multiple PCs now. Suppose a company. The number will definitely increase. Because the number of employees will increase. Everyone needs to communicate with each other. Everyone is on the same network segment. If you want to connect multiple devices. Middleware. So the first hub appeared. Connect multiple devices. The hub was the first of its kind. We use this device. Start connecting. After connecting, we need to know what the hub is based on for data forwarding. I just told everyone. It will perform flooding when it receives the data. But why flooding? How did you know? The data forwarding of the hub depends entirely on its current interface card. Under this interface, you can feel the voltage swing value under the interface. As long as there is data going through. Under the interface on this line. I feel that the data is coming now. Then the hub will receive. And carry out flooding. Bridge is a name. It is a switch with only two interfaces. The processing action of the hub for data is flooding. Flooding means that the data ports other than this receive port. Copy all and send a copy. Here's how it works. So when the hub forwards, no matter what the data, it doesn't care where it goes. As long as the data comes, it will flood out. So actually, it cannot be called a network device. It is just a product of the physical layer. Because it has no CPU. It does not need to calculate. This is how it forwards. And let me emphasize one more point. We also said, if the data sent by PC1 is now, send it to PC2 here. It cannot be sent out at the same time. Data conflict. Therefore, the work efficiency of the hub will be relatively low. The concept of conflict domains we talked about before. We won't talk today. Today we mainly talk about switches. The abbreviation is usually SW. Switches work differently than hubs. Based on physical hardware. Everyone must first remember. For switches, each interface of a switch is a collision domain. Different interfaces are different collision domains. Then it means collision domains are actually small at the same time. There is only one line like this. So now receiving and sending data has no effect. PC1 sends data. PC2 can also send. For switch ports, you don't need to understand why it is different from the interface of the hub. This is an improvement based on physical hardware. That's what's on the hardware level. We only need to know its logical concept. And the switch's interface has a behavior. Self-negotiation behavior. Its interface can realize the negotiation of working mode. For example, the switch is connected to a hub. The hub interface is a half-duplex mode. The switch is in full duplex mode. Switches can be compatible to small. It can also be turned into a half-duplex mode. This switch is connected to a switch. The peer interface rate is relatively small. Its interface rate is relatively high. It can accommodate the other. Negotiate to a rate consistent with it. Backward compatibility. Therefore, the interface of the switch can be negotiated automatically. Each interface of the switch is independent. Then please pay attention. Once each interface is independently, it means that the data of one interface of the switch will no longer be perceived by other interfaces. So how does it work? How to forward data? We just mentioned the MAC address table. For switches. Actually, it's like a brain. This brain is the MAC address table I just mentioned. I'm going to make a logo for the PC. This is PC1. The MAC address of PC1 is AA. This is PC2. The MAC address of PC2 is BB. This is PC3. The MAC address of PC3 is CC. This is PC4. The MAC address of PC4 is DD. Let's simulate data sending now. Suppose PC1 wants to send data to PC2. Then they have to complete an encapsulation of the source MAC and the destination MAC. We talked about. There are two encapsulation methods at the data link layer. One is called E2. One is called 802.3. What we use most now is the E2 package. Now the data link layer is going to be encapsulated. The encapsulation is the Ethernet 2 standard. It has a parameter in it called SMAC and DMAC. Source MAC and destination MAC. Now PC1 is going to visit PC2. Source MAC is AA. The target MAC is BB. Then if such a data is generated, prove that they have made an ARP request. Already got PC2 MAC. This data wants to be sent to the switch like this. Then let it help perform the forwarding. For switches, it received a data. First it has to learn the MAC address. That is, the switch will record the source MAC of the received data frame and the information of the incoming interface. Now this data is sent from this PC. Enter switch. The interface of the switch itself is numbered. For example, this is the interface 1, interface 2, interface 3, interface 4 of the switch. It learns locally. It only needs to receive a data from this interface. It will look at the source MAC in this data and record it in the local MAC address table. So it will now record a interface 1 corresponds to the MAC address AA. It learns like this. The first behavior after it receives the data is called learning. The next behavior is to forward. For forwarding, now it behaves differently. If it receives a data, it is a specific device to be sent to. For example, now it needs to be sent to PC2 specifically. Then it will look at the MAC address table locally. If the MAC address table has, then just retweet. There is a parameter in the MAC address table. Known unicast data frame. Unicast means this data is sent by PC1 alone to a certain device. That is, sent to a certain MAC address alone. And look up the table. If there is, it means that this data can know a clear destination. Known unicast data frame. If you know it, directly look up the table and forward it. What if you don't know? Now it's going to BB. But this doesn't have this BB. Then what should we do? If there is no that for this switch. Unknown unicast data frame. Now where does this data frame go? It doesn't recognize the purpose MAC. So now it will perform flooding. So if a data really comes now, it doesn't recognize the destination MAC. Then it will perform flooding. The action of flooding is to send a copy from all other interfaces. It's the same as the hub just now. It will also send. But you have to pay attention to the difference. The difference is that if there is one in the table, it will be unicast forwarded. Flooding if there is no table. If flooding, PC2 received. It will reply after receiving. When replying, this data enters the interface of the switch again. It learned again. After learning, its MAC address table can be filled. Then next time when the PC sends it again, it can look up the table and forward directly. This is how the switch works. Received a unicast data with a very specific destination. See if there is such a purpose MAC in the unicast data table. Check the table if you have. Flooding if not. After flooding, the device has finished learning. You can check the table next time. This is a processing action for unicast data. We may also have some broadcast messages. Suppose the destination MAC is now all F. When PC1 communicates with other devices for the first time. But I don't know the MAC of other devices. It has to send an ARP broadcast. Then on to the switch. The switch has received a broadcast data. Then don't think about it. Absolutely direct flooding. So you will find. The switch will also perform flooding. But it's not mindless flooding like a hub. Received broadcast or unknown unicast will cause flooding. If you receive a known MAC in the table, it looks up the table. So this is one of the places where switches are better than hubs. It has a forward appearance. Multicast we are not discussing now. Radio is for everyone. Multicast is for a certain group. So if the switch does not enable any functions related to multicast. In fact, it does not know whether the equipment below is added to the group. So you can temporarily consider it the same as broadcasting. You will learn multicast when you reach the IE stage. We don't learn this technology now. Let's make a brief summary. For switches, it doesn't actually care about the IP address of the device. It does not care what network segment the device is. It only sees the second layer when looking at the data. Switches work at the data link layer. That is the second floor. Routers work at layer 3. After it receives a data. To decapsulate the message. To which level? If it demolishes the second floor. After reading the lookup table. Re-encapsulate the second layer before forwarding. Then it means that you only look at the content of the second floor in the whole process. Don't look at the third floor. This is called working on the second floor. For routers, after receiving, must see the second floor. First of all, the destination MAC is sent to it. Yes. Look at the third floor. In the third layer, we need to look at the destination IP address. Then perform corresponding routing function addressing and forwarding. So a router is a router that works on layer 3. For switches, work on the second floor. So all the IP-related stuff at layer 3. It doesn't care at all. Here are some differences between switches and routers. When we talked about routers earlier, basically all related to IP. The switch is not related to IP. I will make a simple explanation. If the interface of the switch receives a data, then it finds this data. It needs to be sent out from this interface. Then the switch will perform an action at this time, called discarding. It doesn't want this packet. So under what circumstances would such a behavior occur? We will not explain at this stage. When you reach the IP stage in the future, you will learn about layer 2 loops. When you encounter a loop, can understand this sentence. Certainly. If it receives a message, failed to pass the verification of layer 2 FCS, it also drops. So actually the switch it works is simple. or retweet, or flooding, or discard. Let's take a look at the PPT's explanation of this. Let's sort it out. The first is flooding. Under what circumstances will we flooding? The switch received a data from an interface. If this data is a broadcast data, the switch is directly flooding. If the data is a unicast data, and there is no corresponding destination MAC in the MAC address table, then exchange chance flooding. So what is forwarding? The switch receives a unicast data, and there is this in the MAC address table. Then it forwards. And what is discarded? It's what I just told you. The switch finishes receiving data from an interface. Also send out from this interface. It will discard this data. This is the switch forwarding behavior. The switch also has a working behavior called learning. That is, learn autonomously. The switch can learn automatically. You don't have to configure it. So some people will say that the switch can be used when it is turned on. You don't need to configure it. That's why it works by itself. Here's some of how the basics of the switch work. Next, these are: forward data frame, the initial state of the switch, learn MAC address. Let's take a look. Just started without a MAC. Sent a data. Learn the MAC under interface 1. Then broadcast. This is an ARP request. Obviously sent. Host B replies to host C. Learned host C under interface 3. This is the MAC address. It's the same as the picture I drew. It's just that it's painted more professionally. Next we start talking about VLAN. VLAN is called Virtual Local Area Network. V is virtual. LAN is local area network. Why do we have a virtual local area network? Let me first describe an environment. In the future, many devices will be connected to one switch. Suppose a switch is connected to 40 devices. Let's just draw. 40 devices is a lot, because the switch has 24 ports and 48 ports. For example, now a device is infected with a virus. This virus is flooding by broadcasting. Then it will infect all other devices. That is, it now affects other devices intermittently, regardless of whether it is in the same department or not. Everyone is connected on a switch. It causes all devices to infect. For the company's internal, everyone will find. In daily life, some of our businesses also need to be quarantined. I give a simple example. For example, your company's R&D department. Usually there are some research and development data or some samples stored in internal server. There are some PCs in the R&D department that cannot even connect to the external network. There will be a lot of core data in it. For business, any PC is now connected to a switch. Actually, we are exposed to the possibility of information leakage. It's all very common. So everyone will find. If all devices are now connected together, connected to a switch, then relatively speaking, there will be a security risk. Whether it is a security risk, or for our business isolation, the actual demand between departments is not well controlled. We have another solution. Just get a separate switch for each department. When you study, you will have this idea. In fact, this idea is correct. Indeed. But it's that expensive. So often we say from the perspective of cost saving, we prefer to buy a device. Just be able to get the job done. So for us now, we just want a device. Can do some of our traffic isolation. For example, a host has a virus. Less impact on other devices. Same. 40 hosts now. Maybe 8 are from the HR department. 6 are from the sales department. 7 are from the technical department. The business between them can also be isolated. Can communicate directly with each other. But I want to ask you a question. When we were learning VLAN, is often the easiest to confuse with a thing. You may have heard the saying before. Different VLANs are different broadcast domains. There is no connection between different network segments. If you can figure out between different network segments, need to find a gateway across network segments. Going to the third floor is also impossible. Then it should not work on the second floor. Some may think. Just configure different network segments for the following PCs. For example, here is a PC. I am 192.168.1.1. The PC on the right is 192.168.2.1. The two of them don't understand each other. If I now draw different network segments for different departments, they are all connected to a device. They also don't work. VLAN also does not work. Different network segments do not communicate. I simply configure it as a different network segment. It doesn't work. So everyone should know. Communication between different network segments. We mean unicast failure. You visit 192.168.2.1 from 192.168.1.1. This is called unicast communication. Then it is the three-layer routing and forwarding. 2.1 according to the destination IP. To query the routing table on the gateway. Then forward. It is a unicast forwarding. Unicast does not work. If the unicast cross-network segment, you only communicate on the second floor. Do not configure a gateway for it. This is absolutely not going to work. But you need to know. Unicast fails but broadcast works. Now this PC1 sends a broadcast data. After the switch receives the broadcast data, its processing behavior is flooding. So as long as this data is a broadcast data, this data can reach the device. As an internal company, virus infections are often broadcast, rather than targeted strikes. Not trying to infect a single device alone. Usually broadcast. So in the form of dividing the network segment, there is no way to isolate real broadcast traffic similar to viruses. It has nothing to do with what kind of data is now. It is related to the forwarding principle of the switch. As long as it is a broadcast packet, even if you divide it into different network segments, where should this data go or where? Everyone can receive. So you have no way to solve this problem. We can only solve it by means of VLAN. Everyone should have an understanding of VLAN. The different broadcast domains it's referring to are. In the future, broadcasting will not work either. This affects the forwarding behavior of the switch. That is, VLAN is configured on the switch. Due to the configuration of the switch, then you can target different interfaces of the switch. Divide it into different VLANs. To control future broadcast traffic. The same is true for unicast traffic. That is, from which interface can all the traffic be sent out? They will not transmit broadcasts between different VLANs. So it can be isolated. I simply give an example. For example, now I divide this interface into VLAN 10. This interface is also VLAN 10. But this interface is VLAN 20. If this device sends viruses out in the form of broadcasting, then it can be broadcast from this interface. But this interface doesn't work, because they cross VLAN. Different VLANs are different broadcast domains. Packets from different broadcast domains cannot be sent out. This is the behavior control that the switch does. A forwarding behavior of its own. So the broadcast domain we're talking about actually means a delivery range of this broadcast message. So the interface of the switch Flooding is the default for broadcast packets. And I tell you, all interfaces of the default switch belong to the same broadcast domain. Different VLANs are different broadcast domains. But unfortunately, by default, the switches are all in the same VLAN. If you want to control it in the future, you need to configure it separately. Okay. What can you understand as a virtual local area network? I configured VLAN on this device. You can understand a VLAN as a virtual switch. I configured a VLAN 10 on these few interfaces. You can understand it as. Now physically you see this switch. It's like cutting it in the middle. For example, the 4 interfaces on the left are assigned to VLAN 10. You can understand that this is 2 switches. It's like cutting the switch in half. This half is a switch. The other half, for example, are all VLAN 20. Although you see it as a device, but actually it has split. You can understand it as a different switch. In fact, there are many ways to divide VLANs. For example, based on MAC, even IP-based, including policy-based. But the one we use the most in our projects, VLAN division based on interface. For example, I now have many interfaces on this device. 1 to 48 interfaces. 48 port switch. We can usually divide the 15 interfaces. From 1 to 15 to the technical department. 15 interfaces from 16 to 30 are assigned to the sales department. 30 to 35 these interfaces are divided into the personnel department. The rest will be allocated to the logistics department. Leave 1 or 2 interfaces for redundancy. This is called interface-based VLAN division. Suppose I assign the technical department to VLAN 10. I assign the sales department to VLAN 20. Assign the personnel department to VLAN 30. This is how we divide. We'll do the configuration later. Let's start with the concept. This division is artificially divided by configuration. Pay attention to my words. Artificially divided by configuration. That is, you need to enter this interface. Then divide it into the corresponding VLAN. Then this interface belongs to this VLAN. It's simple. Between different VLANs, unknown unicast data frames can be isolated. Broadcast frames can also be isolated. Data flooding will not pass through different VLANs. Then one might ask. These 15 interfaces are technical department. Then if there is a virus in one of the data or a PC, what about sending to other devices? Okay. They also get infected. But we narrowed down the scope of the infection as much as possible. Originally 48 devices may be infected. Now you have divided the VLAN. Only these dozen or so devices are infected inside. So narrowed down. It's not that you divide the VLAN. There will be no forwarding of the virus. That's not what it means. You need to know. What we have to do is control as much as possible. I mentioned the structure to you before. Access. Converge. Core. VLAN will be configured in the access below. We will configure gateways of different VLANs on layer 3 switches. But there is no concept of 3-layer division VLAN. This is the access layer switch. They will divide VLAN here. For example, this is VLAN 10. This is VLAN 20. In the future, we will be here on the aggregation switch above. The gateways corresponding to VLAN 10 and VLAN 20 will be configured here. But we will not divide the VLAN in the 3rd layer. VLAN is a concept belonging to the 2nd layer. So, this technique is very common in corporate networks. In the corporate network, switching technology is much more common than routing technology. Because every enterprise must have a switch. But each enterprise does not necessarily have multiple routers. This is the application direction of their technology. This is a flexibility of what we call VLANs. That is, between different floors. We can achieve. Different floors can communicate across switches. Let's discuss how VLAN is implemented. I now ask you a question. Port of this switch. Different devices are connected under it. For example, now both of them are not in the same VLAN. Then please. The device on the left acts as a PC. Does it know whether it is in the same VLAN as the device on the right when sending data? Okay. It doesn't know. So for end users, we only guarantee the most basic data communication. Specifically, what VLANs are they? It doesn't care. So when the PC is actually sending data, it doesn't know which VLAN it is in. It is totally unknowable. The operation of VLAN is configured on the switch. It is a technology deployed on the switch. Let's take a look at the process. For example, now PC1 sends a broadcast ARP. Suppose it wants to ask a user on the same network segment 1.2 of this MAC. Because we did not configure the gateway, we will not go to the third floor for now. The device on the left sends an ARP to ask the device on the right. The switch received the ARP data. How does it tell which VLAN it is based on this data? For example, I now assign 1.1 to VLAN 10. 1.2 in VLAN 11. They do not belong to the same VLAN. Then this data should not be forwarded. Although it is an ARP broadcast. But it belongs to cross VLAN. Then how does it know that this data belongs to VLAN 10? Everyone think about this question. The data sent by the PC does not know what VLAN it belongs to. I have to operate on the interface of the switch. That is, data is sent to the switch here. When coming in from the interface, we want to add a tag to this data. It is a field. The above is a standard Ethernet 2 message. A total of 18 bytes. This part is the frame header and frame tail of the second layer E2. Data is the data part. This tag is inserted between the two of them. This type indicates what protocol the upper layer is. This is the destination MAC and source MAC in the second layer. And checksum. Then the overall tag is embedded. Embedded in the overall data frame. The tag is not just a VLAN ID. It contains a lot. But these things are not very important. First there is a TP ID. It represents the 802.1 queue we will talk about today. 802.1 queue is also called .1 queue. We will configure this thing when we do configuration today. It is a data encapsulation standard. Is a type of publicized tag. Cisco actually has its own proprietary, called ISL. But we hardly use this now. In fact, the proprietary technologies of various manufacturers are not used very much. We are now using public. So it identifies the what kind of tag type do we use. Further down here there is a priority. It represents the priority of VLAN data. In the future, you will learn the IE stage. Learn this field when you learn QoS. Let's not look at this stage. Further down is CFI. It represents whether this frame is a standard format. A CFI of 0 represents the classic format. A CFI of 1 represents a non-classic format. It's almost classic now. So we don't need to look at these parameters now. The most critical is this VLAN ID. This is the switch. This is a PC. PC sends a data. When the data arrives at the switch interface, the PC will carry the VLAN ID. Then there is a 12B written in the VLAN ID. Represents 12 bits. VLAN ID has a range. 12 in total. Each bit has two values 0 and 1. This represents the number of VLANs you can create on the switch. You divide an interface into a VLAN. A data enters this interface. Enter the corresponding VLAN ID. This VLAN has a range. Each bit has two values 0 and 1. There are 12 bits. A total of 2 to the 12th power. A total of 4,096 combinations. That is a total of 4,096 VLANs. But 0 to 4095. This is a total of 4096. Start from 0. Computer languages start with all zeros by default. So it ranges from 0 to 4095. Among them, 0 and 4095 cannot be used. The VLANs we can create are 1 to 4094. This is the range of VLANs we are able to use and create. Remember this. You have no way to create a VLAN larger than 4094. In addition to the VLAN ID we mentioned above, there is another concept. Link type. Let's go back to this picture. For example, we are not giving this device an IP address now, regardless of whether it is a network segment. Assume now go through layer 2 communication. The data arrives at the switch here. Since the behavior of this tag is done by the switch, then think about it. It sends this data to the PC on the right with this tag. Assuming they are both in the same VLAN. Can you send it over? Okay. This is not allowed. Let's take a look at this picture. First you need to know. PC can't recognize tag. I had a student ask me a question before. PC does not recognize the tag. Then don't look at this field. Okay? Just skip it. What I want to say is, our equipment is not so smart. The data frame read by the device is 01010101. A normal data received by PC. After reading the destination MAC and source MAC, you should continue to read type. So if the device sends a data frame with tag, other devices will interpret the data frame according to the type. Then it will find that it does not understand. Because there are 2 bytes in the original type. The first 12 bytes have been read. The 2 bytes of type should be read. As a result, these 2 bytes have been read. It found that this does not seem to be type. Then it means that the data frame cannot be understood. If you don't understand, there is no way to read this data frame device. If it can't be recognized, it can only be thrown away directly. Because reading data is read one by one, including the type in the second floor of our study. The protocol in the 3 layers. It's all about pointing out what the upper layer is now. For the sake of, after reading the second floor, if the 3rd layer is the IP protocol, to read one by one field in the IP header, there are rules. So we often say, the lower layer indicates the upper layer, is for upper class service. When data is read, do you know what kind of data encapsulation standard to read the upper layer data? So this tag is sent to PC. It has no way to recognize. This packet can only be lost. Therefore, it cannot be sent to the PC with the tag. This thing is only recognized by the switch. I said it before. VLAN is deployed on the switch. Only the switch can recognize it. The router can also recognize. But you have to do other configuration. Today we will talk about how to configure. So what we should do is tag the data when it comes in. For example, type a tag 10. In the future, this interface will also be tag 10. Data to be sent. Then when the data leaves this interface, remove this tag 10. Equivalent to. You now want to identify whether the 2 of them are in the same VLAN. Then both interfaces belong to VLAN 10. Tag when you come in. Then when the data flows in the switch, it carries the tag. Remove the tag when you come out. Then send to the terminal, so that they can be dealt with accordingly. It is reasonable to be able to do this technology. Otherwise, the technique is useless. All I want to say is, after we divide the VLAN, each interface will have its own link type. Different link types have different processing behaviors for data. Let's talk one by one. In fact, Cisco is better understood. Cisco only has two link types. The first is access mode. Access mode is used to connect to PC. Before talking about access mode, I should mention two other things. First of all, you need to know, the data frame sent by the PC is called the original frame. It has many names. The original frame is also called the blank data frame. Means data frame without tag. The data frame sent by the PC is always a data frame without tag. For switches, the switch will be flooding. The flooding principle of the switch will be on all except the receiving port. Flooding of other ports belonging to this VLAN. We just said, the switch receives data if flooding. Then it is all interface flooding. Because all interfaces are in the same VLAN by default, called VLAN 1. If the VLAN is divided in the future, an interface has received a data. For example, this unknown unicast is a broadcast. It will only flood the ports belonging to this VLAN. As for how to configure the port VLAN, we will demonstrate. For access mode, we'll connect some end devices, such as computer, server, printer, camera, etc., including future dedocking routers. In fact, we use the most access mode, because the router is a layer 3 port by default. It also cannot handle VLAN-related content. And for each interface, both directions, there are data receiving direction and sending direction. This sentence we will encounter in the future in the study. We are in the NA stage. In addition to the VLAN we talked about today, when it comes to ACL in the future, there will be the same data. We have received direction as well as send direction. One might ask, does the full switch have VLAN? The full switch has a VLAN 1 by default. A switch for dummies is also a switch. The default port of the switch belongs to VLAN 1. It also has its own VLAN. But it's just that it can't be configured. You can't configure other VLANs for it, since the data sent by the PC does not carry the VLAN ID. Then the data is inside the switch. How can I forward it with an ID number? We are through the VLAN ID of the interface. So the default port of the switch belongs to 1. After the device is received, the tag is 1. Let's draw a picture to explain. This is a switch. A PC is connected below. PC now wants to send data. It is connected to an interface of the switch. I assign this interface of the switch to VLAN 10. And it is connected to PC. The connection terminal is access mode. Now access is going to receive data. When it receives data, there is a specification. First look at whether the data has a tag. If no tag, then I'll tag it. This tag is the current VLAN 10 tag. If a data is received, it has tag itself. Everyone will find it strange. I said to connect the terminal under the switch. And if access mode, computers or printers are connected under the switch, they should not be switches. How can I send tagged data to VLAN? This is also very simple. I will give you a simple example. For example, now this interface is connected to a PC or a virtualized server. Either now this PC or virtualized server. I opened a virtual switch for it. It is actually the same as a normal switch. If I now let it bridge the local NIC, then there is a switch here. If auto-negotiation is enabled on both ends, they can even auto-negotiate port. For example, this is an access interface. The data comes in with a tag. I let it bridge with the local network card. So finally there is a switch connected here. Then it can be sent with this tag. So there is also something called VLAN jumping attack. I open a virtual switch in the device. Negotiate with the above interface to become a trunk. This is VLAN 10. As long as VLAN 10 is allowed to pass through, its interface is a VLAN 20. It can skip VLAN restrictions and communicate with hosts below. It can all be done. But I haven't seen this thing in the project. In theory it is possible. I'm just giving you an example. PC can also send out tagged data. We are now because of the technology involved in virtualization. So many things are not so absolute. It is possible to receive tagged data. What if there is a tag? If you receive a tag with VLAN 10 now, then it receives and does nothing. That is, do not remove the tag. Any interface will never strip the tag in the receive direction, just to see whether to accept. If it belongs to other VLAN, then don't. If a VLAN 20 message is sent, it will not be accepted. This is a specification of it. Then let's draw. This data is sent now. Then tag it with VLAN 10. To be posted later. Send in our exchange. At some point it arrives at another interface. This interface is also VLAN 10. It is also an access mode. It is also connected to a PC under it. So what is its forwarding principle like? How does access operate when sending data? Very simple. When sending data, first look at the tag in this data. Is it the same as the tag of this interface? If this tag is consistent with the VLAN of this interface, should send, and will strip the tag before sending. If this tag is inconsistent with this interface, don't send. Here's how it works. So we see if it's consistent now. The data comes in and is tagged 10. Walk in the switch with tag 10. Finally, we will query the MAC address table in the switch. And the MAC address table also has the VLAN to which the corresponding interface belongs. So I can locate this interface. And I found that this interface is also 10. Then it is now consistent with this interface. So strip the tag and send. What comes out is a complete blank data frame. It's a simple process. Finally, the data of the original frame is sent out. For two PCs. What they receive is neat. They feel like the two devices are connected like this. Data forwarding. So for the middle. All about VLANs they are unaware. We'll get to that later. A router is connected to the switch. For routers. If you connect to the router normally in the future. For example, this is a switch. This is also a switch. A router connected to the switch. Then the port of this switch should be access. Because the final docking is a layer 3 interface. Layer 3 interface does not know VLAN. So you have to make sure. This tag must be removed when the data is exported. If even a router. In fact, it can also be identified. But you have to turn on other functions. Next, let's see how to configure. This thing is not difficult. This is 3 devices. It is now on the same network segment. Let's see if the same network segment can't communicate today. They are both 10.1. We will configure the mask to be 24 bits later. They are all on the 10.0 network segment. But both of them are VLAN 10. It is VLAN 20. So wait a minute, we divide the VLAN. Divide on these three interfaces. After dividing it should be. Both of them can pass. But it doesn't work with both of them. Because originally if we did not do any configuration, all three of them should be able to pass. Because they are on the same network segment, the switch does not need to be configured. Learn automatically. Then it's straight through. But after we divide the VLAN, it doesn't work. Let's see how they can't work today. Okay. Let's do some simple configuration. When we talk about the trunk later. Another type. Let's demonstrate access first. Device boots up. This is PC1. Give it an IP address. 192.168.10.1. 24-bit mask. PC can be configured like this. Just enter 24 later. You can also configure the full mask with. Let's take a look at the complete mask of the next configuration. Then PC2. 192.168.10.2. We can also configure like this. 3, 255 and 10. This is also possible. Next. PC3 will not be configured first. Let's look at the switch first. We come in first. Everyone will find. Inside Cisco. When the switch comes in. No need to manually enter NO first. You may be a little uncomfortable. For switches. After changing the name. Let's check its VLAN. Do show VLAN brief. Okay. Now the switch has a VLAN. Don't worry about these below. Let's just look at one. There is a default here. Then the switch is created by default. What do these all refer to? If you create a switch here. This has a default Ethernet port. It's a 4x relationship. If you write one, it will create 4 interfaces. Then actually, these are the 4 interfaces we created. All 4 interfaces now belong to VLAN 1. You did not configure anything. But these interfaces have their own VLAN ID. Is VLAN 1. All we have to do next is put 0 and 1 into VLAN 10. Put 2 into VLAN 20. That is, put these 3 interfaces respectively where they should be placed. First we have to create the VLAN. VLAN 10. VLAN 20. After creating, I strongly recommend that you do this. We can give the VLAN a name. Let's say it's called PC. PC is equivalent to adding a note to this VLAN. Let's check this VLAN. Show VLAN brief. It will have a name in the suffix. Behind this VLAN 10. It is VLAN 0010. This is a way of expressing. After 20. A PC is written here. This is the name we just gave this VLAN. For example, if you want to assign these VLANs to the technical department, just write a technology for VLAN 20. You write a financial statement for this VLAN 10. While you are viewing, the various departments can be divided according to these names. Check what VLANs the switch currently has. There was only VLAN 1 just now. Now with VLAN 10 and VLAN 20. This is what we created. After creating, we are now going to divide these interfaces into different VLANs. Enter configuration mode. First enter the 00 interface. That is, the interface of the switch connected to PC1. It belongs to VLAN 10. So how to change it? I teach you a command. Switch port mode. I enter a question mark. There is a private VLAN here. This you will learn in the NP stage. Then there is an access and a trunk. These are two types. There is another one that everyone is using now. .1Q tunnel. This you will learn in NP. We only learn these two in NA. Let's change the access now. We divide it into access types. Then after changing to the access type, we need switchport access again. We need to assign VLANs to it. VLAN 10. We can now look at this configuration. Do show run interface E00. Okay. Let's take a look at its configuration. We first changed it to an access mode. Secondly, change it to VLAN 10. Here is the configuration for this interface. Then we exit. We also perform the same configuration for the 01 interface. The 01 interface must also be in access mode. Switchport mode access. Then switchport mode access VLAN 10. When we are done with this now, let's exit and take a look at the situation of the VLAN just now. Show VLAN brief. This is VLAN 10. Interfaces 0 and 1 in VLAN 10 have entered VLAN 10. Just these interfaces are in VLAN 1. After we divide, these two interfaces are in VLAN 10. Then we now first look at ARP on PC1. Here it shows that the ARP table is empty. Because we don't have data access right now. I can give a simple explanation. It's not working now. Both of them are VLAN 10. They don't span VLANs yet. We haven't configured yet. Let's review the process. For example, PC1 now sends a data here. Hit a tag 10. But let's not talk about the tag issue. What I want to ask you now is, for PC1. PC1 is 10.1. PC2 is 10.2. PC1 holds its own mask locally. Add the IP address of the peer. Calculate whether PC2 and PC1 are in the same network segment. Should be the same network segment. Then, if PC1 accesses PC2, it is now going to send an ARP request. That is a broadcast packet. So now this message is sent. Sent to this switch. This switch first starts learning. Under this interface, I learned a PC1 MAC. After that, it is flooding the interface to which VLAN 10 belongs in the current device. Because it doesn't know yet. Where exactly does this broadcast packet go? But it's flooding. Flooding from its native interface belonging to VLAN 10. It localizes these two interfaces. Except that it received from the 00 interface. Then the broadcast data packet sent will only be sent from the 01 interface. That is, it will look up representations from here. Then post it. So we just finished creating VLAN 20 here. We now divide this 02 interface into VLAN 20. Let's configure. First enter the E02 interface. Switchport mode access. Switchport mode access VLAN 20. It is different from other equipment VLAN. Show VLAN brief. Check it out. Now for interface 2. It is already in VLAN 20. We also configure an IP address for the third device. 192.168.10.3. We now have 3 devices in the 10.0 network segment. Let's take a look at the message next. I asked PC1 to wait a while to ping PC2. Logically speaking, it works. Because VLAN 10 comes in here. Our ARP must first send a group. Then from this interface, the ARP broadcast should pass. It should come back with an ARP broadcast from here. After that, our ping packets will pass through. So let's wait a moment to get the packet under this interface. We can get ARP packets. This is the first point. Before we talk about VLANs. If by default all devices belong to the same VLAN, then this interface will also receive ARP broadcast packets. Because we're going to broadcast. Let's see now that the VLANs are divided. Will this broadcast be sent from this interface? So we can see. After the VLAN is divided. Is the broadcast data packet really unreachable? Let's take a look. We get a packet for interface 02. Let's do a demo. Let's get another packet from interface 01. Let's do a demo. This thing is not very important. Just to show you a phenomenon. You have to verify whether the knowledge is correct. Get the data packet of interface 00 and only see the reply from PC2. Which is equivalent to. Now this packet. It is to wait a while to reply. Including the package that will pass through ARP. This is through ARP. This is without ARP. We set our sights on this. Let's try to ping now. We start ping here on PC1. Ping 192.168.10.2. Ping PC2. Then what we should be able to see here. Okay. We see ARP. Same. Let's take a look at the message on the right. It has nothing. We pause. There is no need to read the rest of the messages. This is under the 01 interface. The one on the right is under the 02 interface. Under interface 02. It does not see any ARP packets. This shows that the ARP request is a broadcast packet. Then the broadcast message and the destination MAC should be all F. When PC1 requests the MAC of PC2, it doesn't actually know where PC2 is. So it broadcasts. If it is according to the statement that all interfaces of the switch are in the same VLAN. This broadcast packet is sent like this. Now this interface cannot get this broadcast packet. Because it belongs to VLAN 20. And they belong to VLAN 10. So when a broadcast packet comes in, tagged with VLAN 10, it is not issued from the interface of VLAN 20. So it cannot receive this message. ARP is a broadcast packet. When the virus spreads in the future, it is also a broadcast packet. Then the reason is the same. No matter what packet. I'll call 10 when I come in. Then the interface of 20 will not send out. In fact, we don't need to take a closer look at the content. Just read this message. Okay. We can also check the MAC address table on the switch now. Show MAC address table. We can only see the interface for VLAN 10 here now. That is 00 interface and 01 interface. Anyone know why we can't see PC3? Because PC3 has no data passing through the switch. Send data to broadcast here. PC2 replied. So both interfaces are learned. And they pinged a few times between the two. Messages flow between them. But this interface did not receive broadcast packets at all. It also won't reply. So we now want it to learn PC3's MAC. You should ask PC3 to ping out. For example, I let it ping 192.168.10.1. It definitely can't ping. PC1 must ping PC2 through. But it is definitely not possible for PC3 to ping PC1 and PC2. Not reachable. But it's definitely something that can be learned by now. There is a MAC under the 02 interface. It belongs to VLAN 20. So it is equivalent to learning all three now. But we also verified. Can communicate between them. It doesn't work with it. That's the same reason. It definitely doesn't work with 10.2. Because they cross VLAN. So this is what we call access. This is how it works. Everyone observe this MAC address table. The MAC address table I drew for you just now is relatively small. In fact, each of the MAC address tables is very useful. I just drew the interface and MAC address. It actually has VLAN. That is, how do I know which interface belongs to which VLAN? The MAC address table has. When you divide the interface into a VLAN, the VLAN corresponding to this interface will be written here in the MAC address table. So now a broadcast packet is sent from interface 01. I will only flood from other interfaces belonging to VLAN 10. So I can know. The data only goes out through the 01 interface. So this information is known by the switch itself. Because when it queries the MAC address table, in addition to looking at the interface and MAC address, it also looks at the VLAN. Dynamic means that the current MAC address is dynamically learned. Dynamic learning means that others send data to flow through it. In the future, you can also learn static binding. You will learn in NP. Let's do some port security. For example, a fixed MAC is connected under one port. Or we can also set up to connect multiple fixed MACs. If you connect a switch, there are many MACs below. It's okay too. Bindings also have dynamic bindings. You can also bind manually. This is all the content in NP. Now do a simple understanding. Let's talk about the process. If PC1 cannot access PC3 now, why doesn't it work? Let's review. PC1 accesses PC3. Then first PC1 thinks that PC3 is on the same network segment as it. Then send an ARP request. A broadcast packet goes here. Tag with VLAN 10. Then query the local MAC address table. Because it is a broadcast packet, so it should be on all interfaces belonging to VLAN 10. In addition to the receiving port, flooding on other ports. Only this interface is issued. After receiving this interface, after reading the second floor, we need to look at the ARP in the 2.5 layer. There is a target IP inside. The target IP is to find PC3. But it's 10.2. So it won't reply. So PC1 cannot receive a reply. Because its request message can't reach PC3 at all. So it has no way to communicate with PC3. This is the basic forwarding principle of switches based on VLAN. Next we talk about trunk. If you are interested, you can make this kind of picture after class. This diagram is more basic. When we make a trunk, we directly make a more difficult one. We do one-arm routing. Trunk is the two switches. The difference between trunk mode and access mode is that, first of all, they have different names. It's obvious. Trunk means the main road through which more traffic will flow in the future. In the access mode, it is directly connected to the terminal. Then only terminal traffic will pass through this line. The trunk road is all based on the, like the picture in the courseware. Let me explain their names. Access link means this link is called an access link. This link will only run data belonging to the PC. Whether someone else accesses it, or is it accessing someone else's. This is actually equivalent to an access device. Trunk means now you don't care whether these two devices communicate with each other. The two devices communicate with each other. Or do these two devices communicate with each other? They all flow through the road in the middle. It's like what we call the main road. Now devices want to communicate with each other through it. The interconnection between each other is the same. This is also the trunk. We can also configure it as a trunk. So for us, where data flows through, it is equivalent to a trunk between switches and switches. The connection between the switch and the terminal is an access link. Only run your own traffic. So this is the difference in their names. Let's talk about trunk mode. Simply put, switch to switch. Here's what we call the difference between them. The biggest feature of trunk is it can host multiple VLANs. An access interface can only belong to one VLAN. The trunk can serve multiple VLANs. For example, now this is still a PC. Here is also a PC. PCs are connected to the interface of the switch. Also connected between the switch and the switch. A link used in the middle is called trunk. We connect to the terminal or access. For example, this is still access VLAN 10. Suppose the right side is still VLAN 10. Let's see how it goes. It's easy here. Let's not talk. Data comes in and hits here. There is another package in the trunk. Will be slightly different. We go in here first. Because what we use now is actually the same. After you come in, we will put tag 10 here. Then this data flows through other interfaces. For example, it is going to access this device now. Then the data will now go to this interface. When the trunk is sending data, there will be a difference. First, the trunk will have a release list. For Cisco, it will allow all VLANs by default. But please note, this allows all VLANs. It just means that the VLAN created on this switch will be released now. Assume that there is no VLAN 10 on this switch itself. Then the traffic of this VLAN 10 cannot pass through this interface. You must first create. You just create. It allows by default. Second, we will now check. Check whether this tag 10 is the same as this native VLAN. It defaults to VLAN 1. So now there is a VLAN 10 coming over. It checks whether it is the same as its own one. If the same, it will strip the tag. Send later. If different, do not strip the tag and send it directly. So now I don't modify it. Then come in is 10. If it is 1, send it directly. So actually, we are in the process of data transfer. It was sent back with tag 10. Then this data carries this tag. It came to the interface on the right. The right interface is also a trunk interface. Then when the trunk interface receives data, it will also have some processing behavior of its own. Handling behavior is simple. The first is to look at your release list. Also released all. So, when the data comes, it will receive it directly by default. But still that sentence. VLAN 10 must also be created on this device. Secondly, when we receive the data now, if the received data is received with tag, it just sees if it lets it go. If it is a raw data, that is, blank data frame, without tag, it will mark the native VLAN of this interface. Then you can send data, which is equivalent to the ones coming in now are carrying tag 10. So I took it directly. After receiving this data, continue to move forward. Go to this interface now. Since it is also an access interface, and is VLAN 10. Then here it will strip the tag of VLAN 10 to complete the forwarding. Send to another PC. Then in this process, if there are some other circumstances, for example, now this interface belongs to VLAN 20. There is no interface belonging to VLAN 10 on this switch. But I created VLAN 10. The data will come in. But it can't reach the destination. Because cross VLAN. What we are talking about is that if they are different VLAN, it sure doesn't work. But it's okay to send the data like this. It's just that it can't be sent from this interface. This is what we call a trunk. Let's talk about its configuration in a while. This is how it forwards.